Hey guys, I hope you all are doing good. So, in the last lecture, we covered a lot about propositions, right? So, we have covered what are propositions and the truth tables and how we use logical connectors, right? So, if you have a good understanding about the last lecture, then this one should be pretty easy to understand. One more thing, I made a mistake. I wrote down lecture 9 in the previous lecture, so I hope that doesn't confuse you guys, right? Okay, before I start, I just want to give you a quick explanation of why do we need this entire section again, right? So the basic point is, if you think about it, uh, in very simple words, we want to give some tasks to a computer, right? But so far, we can't just give any task to a computer in English words. We need to find some kind of a way to convert it into some kind of a language that a computer understands, right? So what we do is we have an English sentence. I have a task for a computer to do. I write down it into a code, right? So for example, I'm going to write down how the computer is actually going to solve that problem. So that is exactly why we need this kind of a section, right? What we are trying to do again, we are trying to take a look at English sentences and convert them into logical expressions, right? Which can be evaluated into a computer, right? So this will be a very good section. If you understand it, then it would make things a lot more easier to understand how we write logic in our code too. So let's start with the first definition over here. In this video, we will be covering predicate logic and also quantifiers, right? So a predicate is like a property or a condition that is true or false for different objects. So we're given an example, p of x is equal to x is greater than 3, right? Or p of x could be, let's say, q of x is x is from Canada. So let's try to understand it, right? If you remember in the last lecture, I covered an example where I said this x, it was an example just like this one, is not a proposition, right? Okay, why is this not a proposition? I don't know the value of x, right? If the value of x is 1, then this is going to be false. If it's 4, it's going to be true. But as long as I don't know the value of x, this is not going to be a proposition, right? For a proposition, I need either a true or a false value. So that's the basic concept, right? But this can be a predicate in this case. How do we represent it? We say p of x is equal to x is greater than 3. Now, if you think about it, this is a predicate representation in very in very simple words, it's kind of like a function, right? I input some value into a function and I get an output from it. Now if you think about it, for example, this p of x basically turns it into some kind of a condition saying x is greater than 3. So this is the proposition. Now this predicate becomes a proposition when I input a value into this x over here. So if I say p of 1 would be 1 is greater than 3. Now, this is going to be a proposition. Why? Because I have some values and I can figure out if this is true or false. And in this case, this is actually false, right? Same thing, if I do P of 4, then this is going to be 4 is greater than 3. And again, this is going to turn into a proposition, right? Which is actually true. So the basic point is a predicate is just basically a condition which when I put an input, some kind of an input into it, for example, if I input the value of x in this case, it turns into a proposition, right? This is going to be extremely helpful for us to basically define a lot of conditions or logical connectors. Now, same way, I have this another example saying q of x is equal to x is from Canada, right? Now I can turn this, I can say q, I can input, let's say, John. So Q of John would simply be John is from Canada, right? Now, if I know the person John, maybe he is from Canada or maybe he's not, right? But the basic condition that I know is that this is either a true or a false value, right? Now, usually when you are given conditions, it's usually true that you are provided with the truth or false value, so you don't have to worry about that part, right? Okay. So I hope you have a basic understanding about what are predicates. Moving on, let's try to understand quantifiers, right? So just like I said, now, we need to convert basic English into logical sentences, right? Which we can feed into computers and the computers can understand it and then they can work their jobs, right? So, but another thing that we need to understand is that we cannot keep writing entire English sentences to explain things, right? Or for our equations. What we do is we basically want to make things shorter so that we can represent them in small equations, right? So think about it, right? If I keep writing entire sentences again and again, that would be very tedious, right? So what I want to do is I want to use some logical connectives or some kind of symbols to represent everything that I have. So if you remember from the first lecture, we have introduced a lot of symbols, right? For example, what is a subset? We have a symbol for it. We have the symbol for if something is an element of a set or not, and a lot more symbols, right? In the last lecture, we introduced symbols such as and, or, which is conjunction, disjunction, negation, the condition, and biconditional, right? So these make the sentences a lot more easier to understand. We can represent the entire condition or logical connectives with these symbols. And again, we don't have to write each and every sentence down. We can use the P or Q values to basically represent propositions, right? Just like I said, use capital letters to represent propositions. So basically what we are doing is I have a big sentence and I use these connectives and I just use the capital letters, short it down so that I can still understand it, but it's a lot more easier to write down, right? Okay, so same thing is for quantifiers, right? I think I made a very big explanation for this part, but quantifiers are basically the same thing. It's kind of like some kind of an addition to how we can make our sentences shorter to understand, right? But there's a very important logic in these quantifiers to understand. But let's start with the definition, right? They're basically symbols used in logic to express statements about how many elements of a set satisfy a given property. So in a lot of conditions that we check, for example, when I'm writing a code or when I'm making some kind of a program, right, it is probably the case that I'm checking a lot of conditions, right? And it could be that I'm checking that condition for all the elements that I have, or maybe I'm checking it for a single element, right? So basically, about how many elements of a set satisfy a given property. Now, this property could be anything. If I try to give you a basic example, right, think about this over here. Now, if I want to check are all these numbers odd or even, then I need a way to represent it, right? And that is the representation sign that we have been missing so far. And that is, and these are the two symbols that we use, the for all and there exists symbol. Let's try to understand each one in detail, right? Now, from the word itself, for all and there exists might give you a basic hint of what they mean, right? I'll try to write down a sentence. Okay. I hope you understand this symbol over here. This is the, just like I said, this is the element of symbol, right? We introduced it in the sets. So I said, if you try to read this sentence, I'm saying for all x values in the set of all natural numbers, x is less than 5. Let's try to understand this sentence. What I'm trying to say is all the values in the set of natural numbers are less than 5. But do you think this proposition is actually true or not? And the basic answer is no, right? This is actually going to be false, right? But the basic idea for this representation is for all, I can replace this. Instead of writing for all over here, I can just replace it simply with the symbol, right? For all. So a basic summary of for all is whenever I'm using a for all in my predicate, what I'm trying to say is I'm saying it is true or false for this and that entire condition. For all of x, x is less than 5 means for all the values inside the natural number set, they are less than 5, right? Let's try to give you another example. Let's say for all of x, okay, again, very simple example. For all of x, if you try to translate it into English, what this means is for all the values x, which are elements of the natural numbers, so meaning all the natural numbers, for all the natural numbers, x minus 5 is equal to 25, right? So I'm saying all the natural numbers that I have, if I do x minus 5, minus 5 from them, they should result in a 25. But do you think that's the case? That is actually not the case, right? So whenever it comes to for all conditions, what we try to do is we try to prove if they are false or not, right? I'm going to try to find a condition where this is going to be false. That's the only way I can figure out whether this is false or not. If I'm not able to find any x element where I cannot prove this is false, then statement is going to be true, right? But basically, I'm going to try everything that I can to figure out or try to find I should say, a contradiction to this statement. But over here, it's very simple to understand. I know that x equal, let's say, 36 is a value, right, which I can input over here and it would not result in a 25, right? So it is a counter example to this statement over here. I hope you understand, right? So x equal 36 is a counter example. This is just like I try to say something, I say this is the truth, but somebody comes up to me and gives me a counter example to it, proving their point, right? So I gave you this proposition, you come up to me and saying that if I input the value x equal 36, then this would be false, right? Making this entire proposition, or I should say this entire predicate, to be false, right? So just a quick summary. When it comes to for all, I'm checking all the elements and I need to check that the condition is true for all the elements, right? Even if I find one example where it's false, then the entire condition, the predicate, is going to be false. Now let's try to understand that there exists. Okay. Now, again, I'm going to give a basic example, right? Okay. First, I'm going to read this sentence, what it means in English, right? I'm saying there exists a value x. I'm saying there exists a value x, which is an element of the natural numbers, such that x minus 5 is equal to 25. Okay, let's try to understand that there exists. If you try to understand it in very simple words, I'm saying there is a certain value x in the set of natural numbers such that if I do x minus 5, it is equal to 25, right? So what I need to do is, in order to prove this point, I just need to find one example for it, right? And can I find a one example? I actually can, right? Which is going to be for x equal 30, will be, right? I found a basic example. So I'm saying I first gave you this condition over here, right? I'm saying there exists some value x such that x minus 5 is equal to 25. And I also gave you an example over here. So in this case, in the there exists case, I just need to find one example for the case, right? If I cannot find a single example, then only this entire condition is going to be false. But if I find just a single example, this condition is going to be true, right? But it could be the case that I can find multiple elements in the case. It doesn't matter, right? But the basic point is I need to find at least one example in this case, right? So I'm also going to write this down over here. So for all, to find one counter So I hope you were able to understand how the quantifiers work. Quick summary, for all means for all the elements, the particular condition is true. There exists means that for a particular element, that condition is true, right? Just a very simple example. Now, there is some property that you need to understand for this as well. So now let's try to understand it. Okay, now let's try to understand what does it mean by negating quantifiers, right? This is a very important property to understand. So by now, I hope you understand this entire sentence, right? This px over here represents a predicate, just like I said, right? So Predicate meaning I input some certain value x into it and it could either result in a true or a false, meaning it turns into a proposition, right? So this sentence is saying if I negate a for all x, p of x, it is equivalent to there exists x negation of p of x. So what is basically happening is when I apply a negation to this condition, right, it basically turns the for all symbol to a there exists symbol and vice versa, right? So it is going to convert this symbol to a for all and a for all symbol to a there exists symbol, right? If you can notice that over here. And it is also going to negate this p of x value. I'm going to give very simple example to explain this. So let's say I am saying now if I try to, let's say I represent this sentence over here, right? Let's say for all x, which are elements of z, p of x, or I should say x square is greater than 4, right? Now, I hope you are able to understand this sentence. I'm saying for all x, which are elements of the set of integers, x square is greater than 4, right? Now, is this true or not? This is actually not true, right? How do I prove that this is actually not true? I find a counter example for it. So in this case, the example would be 0, right? So input 0, 0 square is actually less than 4. So this is going to be false, right? But that's not the point that we need to understand it over here. When I negate this sentence, right, what I'm going to do is, whenever you see a negation across a predicate, right, first you convert the for all symbol or the quantifiers to the opposite quantifier, right? So I'm going to convert this into there exists, right? And then I'm also going to do the opposite of this condition or p of x I've given, right? So negation of this means convert the quantifier and also negate the predicate that you have. This gives me there exists. So if I do it, this is actually equivalent to there exists such that x square is less than equal to 4. This is what it is equivalent to, right? So what happens is when I do the negation of this, I converted this symbol into the there exists one, and I also converted or did the negation of this sentence, right? I hope you understand how I did the negation. In the actual predicate, I was saying x square is greater than 4. Its negation, meaning its opposite, is going to be x square is less than equal to 4. Right? So I hope you were able to understand it. Same thing happens in this case as well. That is, if I do the negation of this sentence, there exists x such that p of x, it converts the quantifier there exists into for all, and we do the negation of p of x just like we did in this part, right? So long story short, when you see the negation, you just need to follow some basic rules, and it should be very easy to solve, right? Okay, so I hope you were able to understand how predicates work. We have a basic representation. In summary, we represent predicates with something like p of x slash q of x. I introduced quantifiers as well. So whenever you have quantifiers, quantifiers help us to prove a point or write down the proposition for either all the elements or a particular element, right? So we have the for all and the there exists quantifier. Now I'll be giving a bunch of questions just like every single video, and I want you guys to solve these questions, and then we will move on to some more complicated concepts, right? Okay, so this time I gave some pretty tough questions, right? But I'm going to explain them in a very easy way. So I think this should be very easy to understand, right? So let's start with question number 1. Given the statement for every real number x, if x square equal 1, then x equal 1, right? So you've been given some tasks that you need to do. Express the statement using quantifiers and logical symbols, right? So let's start with this one. If you try to read this sentence, right, I'm trying to look for some words which I can convert into symbols in this case, right? So I see the word for every. If you remember, this can be converted into the for all symbol, right? for every real number x. Now, if you read this sentence over here, right, what this means is, it basically means x is an element of the set of real numbers, right? This is what it exactly means for every real number x, for all x which are elements of the real numbers, right? So we're going fine until this point. And this sentence, if you remember from the logical connectives we did in the last video, if x square equal 1, then x equal 1, right? This is a conditional statement. And how do we write a conditional statement? We represent it using the arrows, right? So this is going to be for all x which are elements of the set of all natural real numbers, x square equal 1 implies x equal 1, right? So I hope you're able to understand what this basically means, right? I'm saying for all the real numbers x square equal 1, if x square is equal to 1, then x should be equal to 1, right? And this is basically in very simple words, right? So if you try to understand it, I had this big sentence and I converted it into a logical statement, right? Using some symbols. So now the next task is to negate the entire statement. So let's try to do it, right? If you remember, whenever I have to negate a statement where there's a for all, there's a specific way to do it, right? And what it is, so this is the negation of for all x, elements of the real numbers, x square equal 1 implies x equal 1. Okay, how do I negate it? Simply, I convert this symbol into the there exists symbol, right? And this is the predicate that I have, right? If you try to understand it, this is my entire predicate, and I'm just going to do the negation of this entire predicate, right? So what I get is, I get there exists x, which is an element of the real numbers, such that negation of x square equal 1 implies x equal 1. Okay, so this is going to be the entire answer that I get. Now, your question might be, how do you further negate this statement, right? Now, if you remember, this is a task that I leave up to you guys. I told you guys that there's some specific representation that we can do, right? I'm just going to give you the representation. If you remember, P then Q. This is actually exactly the same as negation of P or Q, right? So this is what it exactly means, right? If you remember, we compared their truth tables and we figured out that they're actually equivalent, right? So maybe what you can do is, you can, instead of writing this with the arrows, you can convert it into this sentence, and then you can do the negation just like using the De Morgan's law that we covered, right? So I'll leave this task up to you guys. Moving on. Final question says, is the original statement true or false, right? So let's try to understand it. Original statement says, for every real number x, if x square equal 1, then x should be equal to 1, right? I've been given a for all statement, so the only thing that I need to do is, I need to find a counter example to it, right? One counter example and this entire statement is false. If I am not able to find one, then only this statement is going to be true, right? So let's try to figure it out. Okay, if x square equal 1, then x should be equal to 1. What if, in this case, if you try to understand it, right, it's saying x square equal 1, then x should be equal to 1. But if you remember, if x square is equal to 1, then x can be 1 or minus 1, right? I hope you understand it, right? If I square 1 or negative 1, it is going to result in 1. But according to this statement, for every real number x, if x square equal 1, then x is equal to 1. But this is actually false. Why? Because in the case, it is actually true that x can be 1 or negative 1. So the original is actually going to be false, right? Okay, moving on. Let's try to solve question number 2. Consider the following statements. Okay, I think I've missed the statements, right? So I'll just write them down. So these are the two statements that I have. One is A for all x, which are elements of the real numbers. There exists y. So this is the first one, right? And this is the second one. Now, according to the question, first you can pause the video and solve it if you haven't covered it yet. So let's start with the question now. Consider the following two statements. Explain in simple English what each sentence means, right? It's very important to understand this part, right? It could be that in your exams or just in general, if you're solving coding questions, you get into these kind of situations. So it's very important to have a clear understanding about what they mean, right? Let's try to understand first one. In simple words, if I convert it into plain English, it says for all x, which are elements of the real numbers, there exists a value y such that x plus y equals 0. Let's try to understand what this means, right? What I'm saying is that for all the real values, right, if I have for all the real numbers that we have, there has to be some kind of a value such that when I add both those values, it is equal to 0. That is what this sentence basically means, right? So if you try to think about it, right, do you think this is true or not? For all the values, for all the real values, do you think there exists a certain value for every single value such that it is equal to 0? And the answer is going to be yes, right? Why? Because, for example, let's say you consider the value 2 for x. Then I can consider minus 2 for y, right? If I consider 3 for x, then I can consider minus 3 for y. So if I consider any real value for x, then there exists a negative value of the same value, which will result in a 0 again, right? So I hope you are able to understand it. Moving on. So this is actually true in this case, right? B says there exists x, which is an element of the real numbers, such that for all x, which is also a real number, x plus y is equal to 0. Now, in the beginning, they might seem like very similar sentences, but they have quite drastic differences in both of them, right? Let's try to understand this one now. This basically means I'm saying there is some value x such that for all the values, sorry, I should say, okay, so I made a mistake. This is actually should be y in this case, right? Okay. So if you were not able to figure out, I'm really sorry for this mistake, but this is supposed to be y. So the point is, for all, there exists some value y such that for all x, x plus y is equal to 0. Let's try to think about it, right? What I'm saying is, there is some value y, there is some particular value y for all the real values x such that x plus y is equal to 0. Let's try to think about it. In this sentence, I'm saying there's only a single value x, right? There has to be some kind of a value which I add into any real number and it should result in a 0, right? So if you don't understand it, I would say try to move the video back a bit and try to understand this sentence again. But I'm just going to repeat the meaning of the A part again, right? In the first part, I meant for all the values, there exists some particular value, like some unique for each one of them, such that adding them results in a 0. In this one, I'm saying there exists some value, there is some value such that if I add any real number to it, it should result in 0, right? So there's quite a bit of a difference in both these statements, right? So it's very important to understand. This is actually going to be false. There is no real number which exists, right? Which I can add to all real numbers and it would result in a 0. Can you think of such a number? It doesn't really exist, right? Okay. Now let's try to understand. So explain in plain English what each sentence means. We have already done that. Are they logically equivalent or not? And the answer is no, right? Identify which one is true and which one is false, right? So we have already figured it out. The first one is going to be true and the second one is going to be false. So I hope you were able to understand the difference between both these sentences. So when it comes to questions like this, it is very important that you understand the entire statement, right? Try to read it in English once and then try to understand, try to visualize it in your mind what the statement is trying to say, right? And these type of questions can be very tricky and a lot of students make mistake in these type of questions. So be very steady and be very slow when you're trying to solve questions like this, right? Okay, moving on, let's try to solve question number 3. Given the statement, given the expression, translate into English, right? So let's try to translate into English. I'm saying it is, since I have a negation, I'm just going to translate this entire thing into English statement. It is going to be, it is not true that values x there exists such that x is less than y. Right? Now, this is quite a big sentence. Maybe I could have done a better job into making a sentence out of this, but this still kind of makes sense, right? So, this is the basic translation into English. I haven't, so I know I can solve for this negation, like I can convert this into this, but the question has asked me to simply convert this entire sentence into English, right? And that's exactly what I did. So I said it is not true that for all the values of x which is a natural number, there exists a y such that x is less than y, right? Okay. Now, next question is rewrite the negation using De Morgan's law for quantifiers, right? So we have already solved this part. I think I'll leave this question for you guys, and I'll put the answer into in our comment section, right? Okay, moving on. Now let's try to solve question number 4, right? Given, let the domain be all natural numbers, right? So it is basically the set of all natural numbers. Let's say P of x is the predicate such that x square is greater than x and Qx says x is even, right? Determine the truth values for each of the following, right? Let's start with the first one. For all x, which is the element of the natural numbers, P of x, I need to figure out whether this is true or not. If you remember, when it comes to the for all quantifier, I only need to find a single counterexample, right? And if I'm able to do it, if I'm able to find more counterexamples, that's a good thing. But I just need to find one counterexample to it in order to prove this is false. If there is no counterexample to it, in that only case, it is going to be true, right? So let's try to think about it. It basically says for all the values of x, x square is greater than x, right? So do you think for all the natural numbers, x square is greater than x? It is actually going to be false, right? Why? Consider 1 and 0 in this case. 1 square is not greater than, do you think 1 square is greater than 1? Do you think 1 square is greater than 1? This is actually not true, right? 1 is greater than equal to 1 but not greater than it, right? Same thing is with 0 square is not greater than equal to 0, right? So I have two counter examples to it, which is 1 and a 0. So this is actually going to be false in this case. Moving on, given the part B, it says there exists a value x such that negation of P of x, right? So let's try to convert it into an English sentence. It says there exists a value x which is an element of the natural numbers such that x square, the negation in this case, is going to be x square is less than equal to x, right? This is the negation, right? I hope you understand how I did the negation. This is greater than x, and when I convert it, this is what you get. So let's try to think about it, right? Do you think there is some value such that x square is less than equal to x? And the answer is again yes, right? We already saw two examples. 1 square is greater than equal to 1 and 0 square is greater than equal to 0, right? So since I have two examples for it, what are we doing in a there exists statement? We are just trying to find an example, right? So in this case, it is going to be true. Moving on. Then moving on, let's try to solve part C, right? Given there exists x, which is an element of the natural numbers, such that q of x and p of x, right? So let's try to convert it into English sentence once again. There exists some value x such that x is even and x square is greater than x, right? Let's try to think about it. Do you think that there is a certain value x such that it is an even value and its square is greater than x? And the answer is simply true, right? If I think about 2 or if I think about 4, 2 square is greater than 2 because 4 is greater than 2, right? I can say 4 square is greater than 4, right? So I have a lot of examples in this case, but I don't need a lot of examples. Even if I use a single example for it, I can say that this is true, right? So this is going to be true as well. So I hope you were able to solve all these questions. These were pretty tricky questions. And if I made any mistakes along the way, please let me know. I'll correct those mistakes, right? But that was it for this video. In the next lecture, we will be covering a bit more complicated topics again, right? So I'll see you guys in the next lecture.